Alrighty, now let's do one practice math problem and give you guys an idea of how this stuff works out. Okay, so let's say that we have a sample that is 1 kilogram of silver. I want to take that 1 kilogram of silver and I want to know how much heat is required to bring 1 kilogram of, let's say 300 Kelvin silver to, let me find where I wrote it down. (1,300) Kelvin liquid silver. Alright, now from the second video lesson, I kind of tried to show you that if you look at the temperature and the state of this stuff here, it's going to kind of look like this. Temperature versus time. Solid is going to be from here to here. Liquid is going to be from here to here, and above will be gas. We're not going to worry about plasma for right now, but this will give you the general idea of it. So I'm going to take this 300 Kelvin silver. This is going to be my starting temperature. Now, there's a few steps that need to go on here. I need to take my 300 Kelvin sample. I need to bring that 300 Kelvin sample of a solid up to the melting point of that silver. The melting point of that silver, according to page 487 in your book, is 1,235 Kelvin. 1235 Kelvin. So, it's going to take a certain amount of heat in order to go from here to here. Then it is going to take a certain amount of heat to turn solid 1235 Kelvin silver to liquid 1235 Kelvin silver. So there's a certain amount of heat required to heat it from cold silver to hot silver. There's a certain amount of heat required to turn it from solid silver to liquid silver. And there's going to be an additional amount of heat required to bring it from, well, even though we're talking about very, very high temperatures here, cold liquid silver to hot liquid silver. So there's a certain amount of heat that is going to be required to take it from 1235 Kelvin liquid silver up to 1300 Kelvin liquid silver. Okay, so there's 3 different math problems that I need to do. 1, 2, and 3. Now first of all, I have given you a mass, so therefore I'm going to be using the equation Q equals M delta T C with a lowercase c for this case here. The lowercase c, of course, means that we are talking about the specific heat or the heat capacity per unit of mass. Okay? So, all of the constants that you're going to need for here are either on page 487 or page 485. Okay? So, let me shrink this down, and I'm going to start breaking this down step by step. So, alright, I'm going to label these steps, and I'm going to do them in different colors so you know what's going on here. The first thing that I need to do is take my cold silver and turn it hot as a solid. So, Q equals M delta T C. I'm looking for Q. I know my mass. I technically know the temperature change And I know this is a constant value that is out of the handbook. So Q is the only unknown. That's going to stay as the variable. The mass is 1 kilogram. But what I want to do is I'm going to use the other information that I'm given to try to determine exactly, well, what units I should be using. When I look in my book at page 485, I've got options of specific heat as calories per gram Kelvin or joules per kilogram Kelvin. Now, I am going to prefer to stick in units of joules for right now, because if you flip to page 487, you're going to notice that this stuff is in the form of kilojoules. So rather than converting things through later, I'm going to leave them in the terms that I've got. So silver, specific heat, is 236 joules per kilogram Kelvin. So I'm going to be using kilograms here. So the mass is 1 kilogram. Now, one thing that you're going to notice with me here is I'm going to be leaving the variables in with the math problem. By doing that, it gives me the opportunity to make sure that things cancel out and to make sure that I had the proper units in the first place. All right, temperature. Well, that's final minus initial. My final is 1235 Kelvin. Minus my initial was 300 Kelvin. C. We already said out of the book, the C that I'm looking for silver as a solid is 236 joules per kilogram Kelvin. Shrink this up so I can write it all on here. Okay, so Q equals, well, now I got myself to a math problem here. 1235 minus 300 is going to be 935. So 1 times 935 is going to be 935 kilogram Kelvin, because multiplied together, those are my units, times 236 joules per kilogram Kelvin. Now here's the nice thing. Kilogram Kelvin, kilogram Kelvin, kilograms will cancel with kilograms, Kelvin will cancel with Kelvin. I'm going to end up with units of joules here. So 935 times 236, get my handy dandy calculator out here. Just going to leave this off to the side because I'm going to use it about 150 times here. 935 times 236. Alright, so the Q for this one is 220,660 joules. So now I've solved part 1. Alright, part 1 is done. To get from cold silver to hot silver, I need to add in Q of 220,660 joules. Now the next step, I need to go from solid silver to liquid silver. Now I'm going to shrink this guy down here. I'm going to drag him off to the side. It's important to show all work. Make sure you're very clear with what you're doing and explain it along the way if you can. Alright, I'm going to do this part in purple. I got to take solid 1235 Kelvin silver and turn it to liquid 1235 Kelvin silver. Alright, now in this one it's going to have to be Q equals L M. Now I am looking for the latent heat of, well, I'm going from a solid to a liquid, so this is going to be my latent heat of melting. Okay, I know it seems bizarre, it's going in the opposite direction here. Or wait, no, I'm sorry. Brain fart. Okay, yes, we're going in the right direction here, but if you were going from latent heat of, or I'm sorry, if you were going from a liquid to a solid, you would have to use the same thing, the liquid heat, or the latent heat of melting, even though you're going from a liquid to a solid as well. So it's the same exact thing, it just switches up here a little bit. Okay, so on page 487, it says silver has a heat of fusion of 105 kilojoules per kilogram. Alright, so Q equals, I've got 105 kilojoules per kilogram times my mass. My mass is 1 kilogram. So 105 times 1, kilograms are going to cancel with kilograms. So my Q for this process is 105 kilojoules. So for this step right here, Q is 105 kilojoules. Alright, now the third step, going from a hot liquid to a hotter liquid, I've got to do the same exact thing that I did before. I've got to go through here and look at what liquid silver is. Unfortunately, the specific heats of silver is not listed on here. Now I want to show you a couple of ways that you can go about finding it. Right? Most likely one is to do good old Google. Alright? So, just use what I got open here. Good old Google. Search. Theoretically. And search that in here. Now once again, just like everything else, be cautious of the site that you're using. Alright? Now make sure it's something that makes a little bit of sense. I would be very leery of this one right here, answers.yahoo.com. Just because the person says that they're an engineer doesn't mean that they secretly live in their mother's basement. It doesn't tell you anything. So what I would do is I'm going to look for something that has a little bit more of a scientific backing to it. Wikipedia, obviously. No, we're going to pass that guy up. Engineering Toolbox. I've used this in the past. And let's see if I can get this all right. Okay, so you're going to notice a slight... Oh, no, they actually do have it listed in here. Alright, let's go down to... They have everything in alphabetical order. Sodium, sodium, sesame oil, sulfuric acid, so much for that. Okay, so strike one. Alright, I'm going to pause the video, find the right value, and then I will bring this back. I actually found a really neat website here. I'm going to shrink this down, and I've actually found a metallurgic website where they just have a whole lot of the information that we're actually talking about. So it seems legitimate, so I guess I will talk to you guys about it. I will do a little bit more due research on this, but it appears to be relatively solid. Okay. This is ESPI Metals. They have a really neat thing here where literally it gives you the metal itself, the technical data about it, what it looks like, intrinsic qualities, the crystalline structure, atomic weight, density, thermal properties. Now, here's where things get kind of neat. The coefficient of linear thermal expansion, the exact same stuff we just talked about, is going to talk about it at different temperatures, and it's going to go into a whole bunch of different situations. This is what I was talking about, it not being a linear type situation, where you actually end up getting cubic values, stuff like that, but we can get it to a relatively constant term. It isn't perfect, but it is relatively good. Now, the specific heat of the liquid is 0.310 kilojoules per kilogram Kelvin. So 0.310 kilojoules per kilogram Kelvin. So I'm going to use another Q equals M delta TC. This time I'll use green. No, that's way too bright. I'll use orange. Q equals M delta T C. Q equals, mass is still 1 kilogram. Delta T is final minus initial, 1300 minus 1235. delta T, C was 0.310 kilojoules per kilogram Kelvin. So 1300 minus 1235 is going to give me 65 Kelvin times 1 is going to be 65 kilogram Kelvin times 0.310 kilojoules per kilogram Kelvin. So I just take these two numbers and multiply them together. I had to get rid of my calculator before, so let me pull it back. Clear it out. 65 times 0.310 equals 20.15. And I want to make sure and check my units here. Kilograms will cancel with kilograms. Kelvin with Kelvin. What a shame, I forgot what my number was. Oh, long day. 20.15. And my units are kilojoules. Alright, so for this stage right here, it takes 20.15 kilojoules. So what I wanted to know is how much heat is required to bring 1 kilogram of 300 Kelvin silver to 1300 Kelvin liquid silver. Well, Q, it took me this much heat to go from cold solid to hot solid. It took me this much heat to go from hot solid to hot liquid. It takes me this much heat to go from cold liquid, in essence, to hot liquid. So now all I have to do is combine these together. The first thing you should notice, though, is one of these things is not like the others. One of these things is in joules, the other two is in kilojoules. So that means I need to convert either 2 of these kilojoules into joules or this 1 joules into kilojoules. Now because of the size of my numbers, I would much rather convert joules into kilo. So all I need to do is move the decimal place 1, 2, 3 places to the left, and that tells me it takes 220.660 kilojoules to go from one point to the other. So I get out my calculator again here, add these 3 numbers, 220 plus 105. Well, here, maybe I can do it in my head. 0. 6 plus 5 is 11. 6, 7, 8. 0, 5, 0. 2, 4, 5. 2, 3. 355.810. 340. Heck, I'll get a calculator. It'll make my life easier. Plus 220.660 plus 105 equals, oh, I'm sorry, 345.810. I apologize, 345.810. Okay? So, that is the amount of heat required in kilojoules to bring it from cold metal to hot metal. Okay? Now, this is not very much, it's difficult in its organization, but the math is not difficult in any way, shape, or form. You guys would have been expected to do math like this as a 10th grader. The thing is, now we're looking at what it means in the grand scheme of things. We're going a step beyond. So, with this, I hope you try those 3 math problems, give them a good honest try, and we'll see where we end up. Good luck, and we will see you next time.